two diagrams up on the board right now. One of them has air on the top, glass on the bottom. One of them has glass on the top, air on the bottom. We're going to fire a ray of light from, in the first diagram, air to glass, and in the second diagram, from glass to air. And we're going to see what happens to that ray of light. Firstly, a ray of light that has a small angle of incidence. Right? This angle right here, theta 1, is very small. We're going from a low index of refraction to a high index of refraction. What happens to V? When n goes up, V goes down. Lambda goes down, and theta goes theta goes down. So we're going to find that that angle of refraction is smaller than the angle of incidence. No big surprises there, nothing new there. Let's do the same thing over on the second diagram with the same angle of incidence, the blue one. Theta I is, or theta 1 is a certain value. Because this time, though, we're going from high to low index of refraction, n goes down, V will go up, lambda will go up, and Benton, theta will go up. As n goes down, the rest of them go up. So this time the ray of light is going to bend this way. In the first case, it bended toward the normal line. In the second case, it bended away from the normal line. Make sense? Okay, second ray of light with a bigger angle of incidence. This time theta 1 is bigger than it was before. This time the green ray is going from, once again, low to high index. As index goes up, V goes down, yes. Lambda goes down, and theta goes down. Down. It's bigger than it was last time, but it's still smaller than the angle of incidence. Theta 2 will always be smaller than theta 1 if the index of refraction is going up. Okay, let's draw that green ray over here. Theta 1 is the same as theta 1 was over in the first diagram, but this time n is decreasing. As n goes down, lambda goes up, V goes up, and theta goes up. Excellent. You can see that theta 2 is getting bigger and bigger. In fact, theta 2 is almost 90 degrees right here. Let's do one more ray here. A red ray. Theta 1 is the biggest it's been yet. But we're still going from a low index to a high index. And as n goes up from 1 to 1.5, then lambda will go down, V will go down, and theta will go down. N goes up, all the rest of them go down. Watch what happens over here when I have this ray of light that's going at the biggest angle of incidence yet. We're going from a high index to a low index. As n goes down, V goes, Cameron, V goes what? Up. Lambda goes, Taylor, up. And theta goes up. Theta goes up to the point where theta is actually 90 degrees. This ray of light here just skips along the boundary between the glass and the air. If I increase the angle of incidence even more, so that theta 1 is even bigger than the red theta 1, then theta 2 in the first diagram will still be smaller. Because n went up, theta goes down. In the second diagram, when I have that big angle of incidence that's bigger than theta red, this time we're going to get a phenomenon called total internal reflection. The ray of light doesn't refract at all. It doesn't go into the new medium at all. Rather, it skips off the boundary between the glass and the air and reflects rather than refracts. This phenomenon of total internal reflection will only occur when we're going from high to low index of refraction, the second diagram. Theta 2 in the first diagram is always smaller than theta 1. If you want reflection to take place, theta 2 has to be bigger than theta 1, not smaller. And secondly, it will only happen if theta 1 is bigger than what we call the critical angle. The critical angle is the red angle here, the angle at which reflection begins to occur, the angle at which the refracted ray skips along the boundary between the glass and the air. This provides a nice little summary of what we just said. TIR, or total internal reflection, occurs when light reflects off of a boundary rather than refracts. So instead of going into the boundary and changing direction, it skips off the boundary and reflects off. Kind of like skipping a rock right off of the water. Instead of going into the water, it skips off the water. Total internal reflection can only happen when light goes from high index to low index. That's important. Can never happen the other way around. Doesn't matter how big you make theta 1, theta 2 will always be smaller, and therefore light will always refract rather than reflect. And of course, it only occurs if the angle of incidence is big enough. In other words, if theta 1 is bigger than the critical angle. And the critical angle, of course, we defined just a minute ago, is the angle of incidence at which reflection begins to occur. If you're below the critical angle, well, I shouldn't say nothing happens, refraction happens, as you would expect. But if you're above the critical angle, refraction doesn't happen, reflection happens. Got a couple of applications to show you right now. First one involves a pond. We have a fish at the bottom of this pond. Fish is happy. Got a big tail. Let's make it a smaller tail. Fish is happy because there's no hook in his mouth right now. There's all these rays of light that are coming from the sun, reflecting off of the plants under the water, reflecting off of the soil at the bottom of the pond, reflecting off of the fish. There's a guy standing over here at the edge of the pond, looking into the pond. He sees the fish, but he doesn't see the fish in the right spot. He's tricked into thinking the fish is somewhere other than where it really is. How come? Well, because of these rays of light that reflect off of the fish, millions of them coming into the water from the sun, millions of them reflecting off of the fish, one of those rays of light looks like this. Bounces off the fish, strikes the boundary between the water and the air, and then refracts like this right into the guy's eyes. We expect that refraction to take place because the index of refraction of water, 1.33, and the index of refraction of 1.00 of air means that light is going from a high index to a low index. N decreases, therefore V increases, lambda increases, and theta increases. Theta increases here. Theta 1 increases to theta 2. This ray of light that reflected off of the fish goes right into the guy's eyes. The guy sees the fish, but the guy's brain is tricked into thinking the fish isn't in the location that it's really at, but rather he thinks, or his brain thinks at least, the fish is right here. Our brains assume that light always travels in a straight line. Our brains aren't smart enough to intuitively grasp the fact that light can bend. So when we see light coming at us, our brains initially interpret that as having come in a straight line. So instead of bending like this, we think that this light has come back from a straight line like this, and therefore the fish would be in this location. How many people are golfers here? Even casual golfers? A couple of you guys? I golf sometimes, not very well. Golf once or twice a summer usually. I have 2 clubs, we'll call them, in my bag that are by far the most used clubs, the most valuable clubs in my bag. Number 1 is the putter. I use my putter a lot, like a lot. I remember this one time, I hit the ball onto the green, par 4 hole, hit onto the green in 2. Pretty impressed with myself. Right, I'm going to go for a birdie putt. At worst, I'm going to par. 9. Got a 9. 7 putted. 7 putted for a 9. So I use my putter a lot. The other thing that's in my bag that I use a lot is my retriever, my golf ball retriever. Because if there's water, I will hit it. What I should start doing is aiming at water. Because if I aim at the water, I'm not likely to actually hit it. So that's what I should do. Aim at the water, and it'll end up somewhere else other than the water. But I hit the water a lot. When I hit the water, I take my golf ball retriever and I see if I can see the golf ball. If I see the golf ball, perfect. I stick the golf ball retriever in. But it's hard at first because the golf ball isn't actually where it seems to be. The depth is wrong. So you stick the retriever in, you got to kind of fish around in order to get it because you're tricked into thinking the golf ball is in a place other than where it really is. Just like this fish is in a place other than where it seems to be. This is not total internal reflection, but we're going to get there. Let's take this guy and let's make him back up a bit. So instead of being right at the edge of the pond, now he's backed up here. This ray of light that came from the fish and did go right into the guy's face so that he could see the fish now goes right above his head. He doesn't see that ray of light anymore. So he doesn't see the fish in that location anymore. Now that doesn't mean that he doesn't see the fish because there's millions of rays of light that are coming off of this fish, right? This was just one of them. He no longer sees this ray, however. But there's millions of other rays. Let's take a look at another one. Here's another ray. Maybe this one refracts into his eyes, right? There's the normal line. Maybe this one refracts up like this. Yeah, that could be. Goes back like this. The fish would appear to be somewhere similar to where it was before. Not exactly, but somewhere similar to where it was before. Yeah, that could be, absolutely. But notice that this angle of incidence right here is bigger than this angle of incidence right here. What if that red angle of incidence actually ends up being bigger than the critical angle? The yellow one wasn't. What if the red one is bigger than the critical angle? Well, the light no longer refracts, rather it reflects down like this. The guy no longer sees this fish. You ever notice that? You're standing on the edge of a pond or the edge of a river, and you can see down, you see the rocks down there at the bottom, and you see plants down there, and maybe you see a golf ball down at the bottom of the creek or the river, right? And you back up, and you can no longer see into the pond or the river. You ever notice that? It's because the rays of light that are coming from the bottom of the pond, or the golf ball, or the rock, or whatever it is that you're looking at, those rays of light are reflecting off of the boundary between the water and the air, no longer refracting. There's rays of light that are coming out of the pond for sure. But because you're back so far, those rays of light, Mateo, that are leaving the pond are actually sailing right above your head and you don't end up seeing them. Where would you have to be in order to see this fish now with this red ray of light? You have to be underwater, yeah. You have to be somewhere right here. Where would the fish appear to be if you were underwater there? Mateo? No? Fish would appear to be up there, right? Because our brain thinks that the light traveled in a straight line. Well, clearly you could just look at the fish, right? Because there's another ray of light coming directly from the fish to that spot, right? But the question was, where would you have to be in order to view the fish via this red ray? Okay? So if you're looking up, you would actually see the fish up. But it wouldn't be in the sky because the fish would appear to be above the water, but so would the water, and so would rocks at the bottom of the pond, and so would all the plant life and the dirt at the bottom of the pond. Everything would appear to be up there. Has anybody ever scuba dived? You have? Yes? Glots or?
I got like.
Did you? Okay. I've never scuba dived. I'd love to do it sometime, just never gotten around to doing it. You'll definitely have more experience with this than I ever have. Okay, I know the theory behind it, but never actually done it, right? Scuba divers will sometimes say that it's easy to get confused underwater where you are. It's easy to get confused, A, because you're neutrally buoyant. So up and down is a challenge, right? Like if you're neutrally buoyant, up, down, left, right, it's all the same as far as you're concerned, right? Well, you could look up and look down and see the bottom of the ocean versus the top of the ocean, right? The problem is, if you look up at an angle like that, what are you going to see? Down. When you look down at an angle, what are you going to see? No, you're going to still see down. So no matter which way you look, you're going to see what's at the bottom of the pond. That's a problem, right? You're neutrally buoyant. You don't know which way is up and which way is down based on gravity. You look up, you look down, you see the same thing. How do you know which way is up and which way is down? There is a simple solution to that. What is it? Sorry? Yeah, you go up, yeah. Or just exhale, right? And the bubbles will go up. But initially, it at least I'm told that it can be confusing because disorienting, because up looks to be the same thing as down. Now, I'm also told that if you look straight up, you have no issue. You can see out of the water. There's this circle. There's a circle around you, this kind of this column upwards that will allow you to see. But when you get beyond the critical angle, okay, then the circle disappears and you just see the bottom of the pond on the surface of the water. Does that make sense? Have you ever noticed that? Yes? Okay. Have you noticed the circle? Yeah, okay. Here's another one. This is a diamond, of course, right? The numbers here, don't worry about these numbers. They are important if you are actually cutting a diamond. It's important to get these angles perfect if you're cutting a diamond, but we don't need to know exactly what these angles and slopes need to be. That's neither here nor there for us. Someday, all of you or most of you will either go to buy a diamond or somebody will give you one. I think people that are given the diamond are the lucky ones, right? Because you got to buy one. It's like, it's supposed to be like 3 months' salary or something ridiculous like that. Hey, somebody's giving you a diamond, and you just have to say, okay, thanks. Yeah, I guess you have to say yes, I guess, right, to actually get to keep the diamond. All of you at some point need to know something about diamonds. Whether you're buying one or receiving one, you need to know something about diamonds. There's 4 C's. When they sell you a diamond, there's 4 C's that they'll sometimes tell you about. One is clarity. How clear is the diamond? Is it clear or is it kind of foggy? Obviously, you want a clear diamond. Nobody wants kind of a foggy diamond because it's not very nice if it's foggy, right? The color. Most times there is no color to a diamond, but sometimes there is a color. And if you have a color, it can be more valuable because they're so rare. They're almost always clear. But really, really expensive diamonds can have a natural color to them. So color, clarity, the carat. The carats are the size of the diamond. That's how they measure how big the diamond is. Clearly, that's going to matter, right? The bigger the diamond, the more valuable it's going to be. The 4th one is the cut. So clarity, color, carats, and cut. The cut is really important because if the angles aren't right, the diamond doesn't sparkle the way that it's supposed to sparkle. The exact same material, the exact same diamond, just doesn't sparkle as much. We're going to explain to you why the cut matters, why the cut produces sparkle, and why diamond produces sparkle as opposed to, say, glass or some other fake diamond doesn't sparkle nearly as much. When light comes into a diamond, it usually comes in from above. When it does that, it's going to slow down dramatically, but it's not going to change direction because it's coming straight in. It slows down to almost a third of its normal speed. Strikes this boundary between the diamond and the air. By the way, what's the index refraction of diamond? About 2.42. And the index refraction of air is about 1.00. So it strikes that diamond-air boundary. You need to know that the bigger the difference in n, the bigger the difference in the index refraction between the 2 materials, the smaller the critical angle. So when you have diamond and air, 2.42 and 1.00, that's a pretty big difference in index of refraction, a really big difference in index of refraction. That produces a really small critical angle, which means that it's not very hard for this angle right here to be bigger than the critical angle. If the critical angle is big, which it is if you have, say, glass and air, big critical angle, then it's a lot harder for that angle that we see labeled there to be bigger than the critical angle. So if this is glass, what's probably going to happen is the ray of light refracts out the other side because we haven't exceeded the critical angle. But if this is diamond, what's likely to happen is that we've exceeded the critical angle and the light reflects. Goes over to the other side, strikes the boundary there. You can see the angle between the normal line and the ray of light there. Again, if this is glass, probably refracts out the other side. If this is diamond, total internal reflection because the critical angle is much smaller. You get a lot more reflection taking place inside diamond because the critical angle is small because the index refraction is high. What do we see when light reflects off of this surface? There's where you get a sparkle. When it reflects off of this surface, there's where you get a sparkle. If this was just glass and the light refracted out like this, hey, diamond's nice. It's hard. Doesn't scratch. It's clear. It's shiny. But it doesn't sparkle. It doesn't sparkle because you don't get total internal reflection taking place inside because the critical angle is too big if it's glass because the index of refraction is too small. What if we have a diamond that's shaped like this? Kind of looks like a carrot. Maybe that's where they get the name carrot for the size of the diamond. This is a 1 carat diamond that we have right here that's shaped kind of oddly like a carrot. Here's a ray of light that comes in. Oh, look at that. We're way bigger than the critical angle here, right? Way bigger, the critical angle. There's definitely going to be reflection taking place right there, like this. But what happens when we get over here? We might not be bigger than the critical angle now. So what happens is it refracts out the other side. We see a sparkle right here, but we don't see a sparkle right here. And we don't see the light coming back up at us from below. Remember that first diagram? We saw a sparkle, and then the light returns to our eyes. Here we see a sparkle, and then the light leaves and we never see it again. That's why the cut matters, right? You cut it wrong, it sparkles, just doesn't sparkle as much. You have the wrong material, and maybe it refracts once, maybe it doesn't. Or sorry, maybe it reflects once, maybe it doesn't. Maybe it reflects not at all. Bottom line is you're going to get less sparkling because there's less reflection. Make sense? This little statement here is directly relevant to one of the questions on your unit test. If you have a bigger difference in index of refraction, like when you have diamond and air, versus, say, glass and air. If you have a bigger difference in index, like diamond and air, then you have a smaller critical angle, and it's easier to exceed the smaller critical angle. You're going to get more reflection taking place. Here's one math question. Call it a day. It says, what's the critical angle for water? Let's assume that the second medium is air. There's the diagram. Which way am I going, by the way? If my ray of light goes this way, which one is water, which one is air? Am I coming from air to water or from water to air? Going from air to water? The index refraction of water, by the way, is about 1.33. The index refraction of air is about 1.00. Going from air to water? Who votes yes? Okay, a couple of people yes, a couple of people no. No, it has to be the other way around. It cannot go from air to water. How come? Total internal reflection can only occur when you're going from high to low index refraction. Can't happen when you're going from low to high. Got to be high to low. So it can happen this way. We'll call this N1 and this one N2. Going from water to air. We want to find this angle right here, the critical angle at which reflection begins to occur. Let's say sine theta 1 over sine theta 2 equals Well, let's use n2 over n1. 2 parts of the 4 from Snell's law. Sine theta 1 over sine theta 2 equals n2 over n1. Sine theta 1, let's replace that with sine theta c. The angle of incidence becomes the critical angle. Right, Mateo? Right, Mateo? Yeah. What's theta 2? Yes. Look, theta 2 is 90 degrees. When the light kind of skips along the boundary, and that happens when theta 1 is the critical angle, then theta 2 is 90 degrees. And that's equal to n2 over n1, so 1.00 over 1.33. When you're solving for a critical angle problem, theta 2 will always be 90 degrees, every single time, 90 degrees. What's sine 90? 1. So you can just cross that off if you want, because it's always going to be 1 on the bottom there in a critical angle problem. We get sine theta c is equal to 1.00 over 1.33. Let's do that on our calculator. Let's say the inverse sine of bracket 1 divided by 1.33 gives me a value of 48.8 degrees. Okay, so we have a difference in index of refraction of 0.33 from 1 to 1.33. If we had a bigger difference in index of refraction, would we expect that value 48.8 to be bigger or smaller? We're talking about, instead of air and water, we're talking about air and glass, let's say. Is theta c going to be bigger or smaller? Smaller. The bigger the difference in index, the smaller the critical angle. Okay, what I'd like you to do for homework tonight and for the next 10 minutes of class is to finish up worksheet number 17, please. You've done questions 1 to 7 already. I'm going to have you guys work on questions 8 to 11 for the next 10 minutes, and if you don't finish them for homework tonight.